we're going to talk a little bit about the brain. I think it's fair to say that we are not aware of anything in the whole universe that's more complicated than the human body, and part of that is the immense complexity of the brain, which you'll be happy to know we're not going to go into any great detail. So this is what I'm going to talk about to start off as the background to this. We're going to talk a little bit about the gross anatomy of the brain, and then just a tiny touch on the physiology, how it works, some examples of that. Then talk about the impact of music on the brain, which has been a real surprise. There's something magical about music that we don't really fully understand. And then finally we'll talk a little bit about autism and what it is and how music can impact on that. So let's talk about first the anatomy of the brain. Now, the brain is sort of mushy, it's soft, and it's in two parts, it's symmetrical, but it's been divided up into different areas, into what they call lobes. So there's the frontal lobe, and this is the bit of the brain that you're aware of. There's the parietal lobe, the occipital lobe. So sort of this is the geography of the brain, and then there's the cerebellum. So these are the broad areas of the brain. Now, as I said, it's in two halves. So if you were to slice it down the middle, what you'd get at the other from the inside is a picture that looks like this. And there's this thing called the corpus callosum that joins the two halves of the brain together, the left and right side of the brain. It's a major highway, if you like, of communication between the two halves of the brain. Then the other thing to note from this side is that we're going to talk briefly about is this area called the hypothalamus, which is linked to the master gland, and we'll come back to that in a second. And then there's the cerebellum, and the cerebellum is necessary for coordinating movements. Those of you who play an instrument, for example, we know that it does that because if you do this, you do that very quickly. But if you have cerebellar damage, what you do is this. Okay, so in other words, the cerebellum controls movement. Now, the brain has been found with various studies to have different functions for different areas, and it's worth commenting about these a little bit. When you move your hand, like I'm moving my fingers, that action starts here in the primary motor cortex. On the other hand, I'm feeling this pointer, and that is being sensed here. We're not going to show you today, but there's if you plot in these two areas, if you plot how much of the geography of those two areas the different parts of the body represent, have a guess which part of the body takes about 80% of the whole area. No, the lips take a fair bit. You've seen a homunculus, have you? Yeah. No, have another guess. No. The hands. The hands, because it's very complex. And yeah. Then there's the visual cortex here, and in front of it is the visual association areas where they interpret what we see. Now, you need to understand that you see with this part of the brain, you see with your eyes, but the eyes send messages to the visual cortex. If you destroy this part of the brain, you're completely blind, even if your eyes are perfectly normal. So So what happens is light enters the eye. This is the eye. This has been blown up, but it's that little area there, the retina, the so-called retina. Light enters there and it hits these rods and cones, which are then send electrical signal to the back of the brain. And it's the brain that then interprets what we see. Let me give you an example. You think my jumper is red, don't you? Mm-hmm. Okay? Well, it isn't. The actual reality is that my jumper has a pigment that retains all of the wavelengths of light except red, which then bounces off the jumper and goes into your eye. It hits specific ones of these, which then these ones send the message to the brain. The brain then knows that it's coming from those particular rods and cones and says, oh, it's red, and then produces the image and puts it into your consciousness and you see red. Now, put that in the context of seeing the detail that we see. Isn't it amazing? I mean, that's how it's done. So then we have other areas. We have the auditory cortex that we hear with this part of the brain, and sound is also only in your head. It doesn't exist out there. If there's no ear to hear sound, there's no sound. The radio's on, but there's no one to hear it. There's no sound at all. What is there is movement of air. So what happens? The air is moving, Beethoven is playing, and you get different vibrations which are then sensed by the eardrum here, and it's transmitted through these little bones to this area here called the cochlea, which has a nerve comes out of it. This nerve goes to that area I was showing you before here, and your brain then interprets what the electrical signals again, and you can hear Beethoven or Mozart or whatever you're hearing, right? Then we have this area here, which is the speech center. You speak with this area here, but only from the left side of the brain. So we talk with the left side of the brain. If you have a stroke in this area, you can develop what's called aphasia. Have any of you seen a patient with aphasia who's had a stroke? They try to speak, but they can't. They know what they want to say, but it just doesn't come out. Interestingly, if you get them to sing, they can say every word in the dictionary, because we sing with the other side of the brain, with the right side of the brain. Isn't that interesting? And there's a technique called melodic intonation therapy, where, and no proper study has ever been done, which really amazes me. If you take people that have got aphasia, who've had a stroke, and you get them to sing and sing and sing and sing, and then go into recitative, which is what they do in opera, the sing-song talk, you can teach, potentially, you could teach them to sing, to talk rather. You could teach them to talk again, but no one has bothered to do it. We need some of you to do some research. Those younger ones of you who want to do it.
Is that melodic?
Melodic intonation therapy. Yeah, you heard of that?
No.
Oh, yeah, melodic intonation therapy. Now, the bit that you think is you is this bit here, the frontal cortex, and that's the new part. That's the new part of the brain, in terms of evolution, new part of the brain. The intelligence, the thinking, the I can reason, etc. That's the frontal cortex. One psychologist in the United States says, see, that the rest of the brain is all automatic, and it is the subconscious. And one psychologist in the US has described the relationship of the subconscious to the conscious brain as the elephant and the rider. So you just picture this, a man or woman sitting on top of a humongous elephant going down the road, the elephant represents the subconscious mind, the rider represents the conscious part of the brain, and it tells you the relative strength, because most of our behaviour is actually programmed. Not all of it, but a lot of it. Now, this paper appeared in December 2018 in the New England Journal. They have ability now to study the brain in ways that we've never had before, using what's called functional MRI, where you look at the activation of the brain when you do things, and they're starting to link pathology with areas of the brain and activation patterns. And it's a bit tricky though, because, for example, there's lesions in this part of the brain will give you the same pathology, the same clinical picture, but also the other thing they've discovered is if you damage this part or this part or this part, you can also get the same procedure. And it's confusing because we still don't know the full connectivity within the brain. They're starting to get maps of what parts of the brain are linked to other parts of the brain. The other thing they've found is that they can do maps like this, where the orange and red areas mean that when this area becomes more active, so does this area, that area and that area, whereas the blue-green ones are when these areas become active, the others become less active. It's sort of the converse. And they're starting to understand these sort of things. Now, how does the brain talk to the body? And you can view the body as a vessel for maintaining the brain. Your heart is there to pump blood so that the brain can work. Your gut is there to give you energy in order for the brain to work. And then the brain has to communicate with the body, and it does it two ways. The most important way, I guess, is through nerves. So the signals that the brain generates, and again, just as an example, moving your hand, it started in that motor cortex, it then goes down the spinal cord to here, and then a nerve carries the message to the muscle in the forearm, which then causes contraction and you move your hand. So, and similarly for the legs, etc. So the nerves send signals to the body to make the body move, etc. And then some of these nerves are sensory and they take information back to the brain. That's the other area in the middle cortex, the sensory cortex, that tells you what your body is doing. Have any of you had vertigo? It's pretty terrible when the room starts to spin around. You see, did you see, you may not have noticed that picture of the ear, that there's the cochlea. Maybe I'll go back to it. Oh, here we go. This area here, this we hear with this area here, you notice there are 3 loops. They are hollow inside and they have a fluid level. And inside the lining of those loops are cells that have a filament, a wire. So when you move your head, the fluid level moves and tickles and moves different ones of those cells. They send a message to the brain, and these tell us whether we're lying down or standing up or what the position of our head is. When you get vertigo, when this becomes inflamed and doesn't work properly. And that's so you can start to get a picture of how it works. Now the other way that the brain talks to the body, so there's the nerves, the other way is through hormones. I'm an endocrinologist, so that's where what I do. But the hypothalamus sends a message to the pituitary, which then sends a message to the target glands. Okay, so the thyroid, for example, there's a hormone from there that goes to here, a hormone from here that causes the thyroid to work, to act. And there's another hormone that controls the adrenal glands and then the ovaries, etc. So that's, if you like, a very brief overview of the brain anatomy. Now, how does it work? Well, in the brain there are two types of cells. There's the neurons, which are the ones that signal, and the glia, which are the ones that support these nerves. Now, we have around 100 billion, not million, billion neurons. You have, those of you who are younger than me. I've got less now because I'm getting old. We lose them as we get old. But there's about 100 billion neurons, which and there's about 10 to 50 times as many of the supporting nerves. And this is what a neuron looks like. Have any of you seen a picture of a cell? Mm-hmm. We're made of cells, right? Mm-hmm. But the neuron is a very special cell. It has the same machinery as all other cells, a nucleus, mitochondria, etc., etc. But it also has these structures. It has the dendrites, and these are there for a specific purpose. And then there's the axon, which can be quite long, from there to all the way to there, about this long. And the axon has these the axonal endings. Now these then will link up to the dendrites of the next neuron. Now you can start, that's how the wiring is done. There's a link between the end of the axon of each nerve cell to the dendrites of the next cells. Now ask yourself, how does the nerve cell know which neuron to connect to? If you're going to move your finger like this, how does the right nerve cell here that's meant to contract your finger know which one to connect to in the spinal cord and which muscle to go to? That's all programmed in our genes. Just think about that for a bit. Now, if you think there's a lot of nerve cells, well, they estimate that there's 100 trillion connections in the brain. That's why you can think, that's why you can reason, that's why you can enjoy music. And I reckon that's 1,000 times the number of stars in our galaxy. Now, what controls all of this? Genes. And there's around 2,100 genes that are there just to control the connectivity in the brain. Doesn't that take your breath away? Mm-hmm. And that's what they look like. We've just had a grandchild born 4 days ago, and that's what his nerve, it's a he, Archer is his name, that's what his connections would be like in the brain. He can't do much. Some of it's connected, so he can suck to have his milk, but not much. But by 1 month, it's starting to get more. By 6 months, there's a lot of connections. And by 2 years, look at that, it's a forest, as the nerves connect with each other. Okay? Now, what does music do to all of these connection things? Now, so there's this phenomenon called neuroplasticity. Now, the volume of the brain increases more during the first year of life than at any other time. When we're born, our brain weighs around 400 grams, but by 1 year it's kilogram already, and it continues to grow rapidly in the first 24 months. It's the increase in size of the brain is matched by its activity, and you need to know, you know how glucose, sugar is bad for you? Well, the brain can only use sugar for fuel. There's only one other fuel that it can use, and that's ketones. But it can't burn protein, it can't burn fat, it can only burn glucose. That's why a diabetic, when you give themselves insulin, if their sugar drops too low, they start to shake, and the brain says, eat, and they can go unconscious. And sadly, very young children with type 1 diabetes, it's the terror of all parents that you can die with hypoglycemia if you don't have enough sugar. So the brain can only use glucose for energy. And from the ages of 4 to 10, the child's brain uses more glucose than an adult brain, because it's not only is it working, but it's also got to grow. Now, the development of the brain is genetically predetermined and occurs in a set sequence, starting from the primitive brain, the brain stem, etc. Because all this happened gradually, and what embryology recapitulates is evolution. Okay, and it proceeds from the primitive parts to the higher parts of the brain. Now, this study proved that this was genetically determined. This was published in 2012. They report the heritability of functional brain efficiency during early brain development. They use twins, monozygotic, which means identical, and dizygotic twins, which means non-identical twins, and they concluded that there's a set of genes that is shaping the underlying architecture of the brain. Now, during the growth phase of the brain, you get a bit of overproduction. So the brain seems to make a whole lot of connections, these trillions, but then it says, well, I don't need all of these, maybe we should start pruning back. And not all those connections survive. Many are pruned. And the pruning is part of the problem that may occur in autism, by the way, because there are too many connections in autism, as we'll see in a minute. The control of the pruning is genetically determined, but it's also determined by what the brain is which parts of the pathways the brain is using. If the brain is using a particular pathway, it gets enhanced. But if it's not, if it's misused, unused, it gets pruned. Right? I'll tell you a little aside just so that you can wake up. We went to Cambridge to do a sabbatical, and we were at a dinner one night, and there was a guy sitting opposite me at a college, and I asked him what he did, and he said he was a neurologist, and he studied how the brain prunes connections. I said, oh, that's very good. And then later on I found out he was Charles Darwin's great-great-great-grandson. So there are people who study these things. Now, the decision as to which connections are strengthened and which are pruned depends on input into the brain. And this is the reason why you have to have a rich environment for a child. A lot of stimulation, a lot of colour, a lot of structures, etc. Now, how do we know that this happens? If you do an experiment in an animal, because it would be unethical to do it in a person, and you cover the eye of an animal, so that he can't get any light in, and you let him develop, when you then take the patch off, he's blind in that eye. Can't see anything. Why? Because there's been no connectivity and no message going from that eye to the back of the brain. That part of the brain that we see with didn't develop. So he's blind. And that tells you that unless you use pathways, they're pruned.
Like with people who are born deaf, and if their hearing gets fixed, it can be too late for a lot of things.
Correct. And in fact, you can't actually repeat. Well, except if neuroplasticity is also operating in these areas, you could argue that maybe with time, with constant use, it may, because as you'll hear in a minute, neuroplasticity was thought to only occur in children, but in fact we now know it occurs throughout life. That's the important thing, and this is which is quite exciting, because they're starting to adapt it to people with strokes, etc. You don't give up, you keep trying. It takes a long time, but you have to keep trying. Now, so yeah, that's what this slide says. For many years it was believed that neuroplasticity occurred only in young, immature brain, but now it's throughout life. And in fact, guess what they use to study neuroplasticity? Music. Music. If you look at all the literature, as you'll see in a minute, music is used to study neuroplasticity. And there's evidence that music alters the structure of the brain. Here's a paper in the Journal of Neuroscience. Brain structures differ between musicians and non-musicians. Increased cortical, the cortex is the top part of the brain, representation of the fingers of the left hand in string players. So string players are always using their left hand, enhance the size of the cortex on the opposite side. Superior tactile performance and learning in professional pianists. They have more sensitivity on their fingers, the piano players. Evidence for metaplasticity in musicians. These are all top-notch journals, by the way, so this is real, not what you hear sometimes. Extensive piano practicing has regionally specific effects on white matter development in Nature Neuroscience. Effects of musical training on the auditory cortex of children. And then this one, musical training influences linguistic abilities in 8-year-old children, more evidence for brain plasticity. So this is musical training improving language in children. That means that this is exciting, because it means that you can spill over into other areas. So when you're teaching someone piano, you might get other benefits elsewhere. That's what that means. Now the brain has billions of neurons that are interconnected to many other neurons. The control of these neural connections is genetically determined. Connections that are used are maintained and reinforced, while connections not used are removed. Now, I've got another summary slide after, but I asked the question, what parts of the brain does music activate? And it turns out that this was studied in 2006. How many music centers are there in the brain? And in the introduction of this paper, they say that the traditional view of left-right dichotomy of brain organisation, assuming that in contrast to language, which is one side and singing is on the other, music is primarily processed, they used to think, in the right hemisphere. But that was challenged 20 years ago when the influence of music education on brain lateralization was demonstrated. So it's not just left or right music. when we're hearing music, the whole brain lights up apparently. Modern concepts emphasize the modular organization of music cognition. According to this viewpoint, different aspects of music are processed in different, although partly overlapping, neuronal networks of both hemispheres. So the aim of this study was to clarify the factors contributing to this variability. They conducted a longitudinal experiment comparing the effects of procedural versus explicit music teaching on brain networks. And what they demonstrate was that cortical activation during music processing reflects auditory learning biography, the personal experiences accumulated over time, your previous listenings, etc. That's why I think you enjoy more music that you've heard before. The first time you hear something you may or may not enjoy, but as you play it more, as you hear it more, you get more pleasure. Maybe they used to say because you can anticipate the next note, and that gives you satisfaction. It's not clear that's the case, but anyway, etc. And they conclude that really it's the whole. There are neuronal networks in both sides of the brain that get activated. Now, so this is the reason why music. There are two reasons why music is so powerful when you're talking about teaching special needs children. A, it activates the whole of the brain, and B, can you think of any other activity where you can get repetitive action without being bored? Or you can't. When you're practicing an instrument, you're getting repetitive activity, you're activating those pathways repeatedly and you're boosting them. So this boosting is really important. And on top of that, we now have this evidence that there may be spillover into other areas. So this brings us then to autism. Now, typically children that are on the spectrum have problems in three key areas. First of all, there's communication, both verbal and non-verbal. They have difficulty communicating with you. There's social awareness and interaction. They don't seem to be. We seem to have it as an innate ability to understand that we need to be social, to say hello, how are you? You don't have to actually specifically teach that to a child, they pick it up. But if you have autism, it seems to be difficult for whatever reason that is. And there's difficulties in playing imaginatively. They're more concrete in their playing, and they have narrow interests. Now, there is a spectrum, and on the one end, there's Asperger's syndrome, so mild autism, if you like, where there is being called Asperger's syndrome, but they share common things. Both have problems with social communication and narrow interests. Where they differ is in Asperger's syndrome, IQ is at least average and sometimes astronomical. It's thought that Albert Einstein was on the spectrum. He had Asperger's. If you go to Silicon Valley in the US, all these people that are really clever in programming, etc., a lot of them have got Asperger's. And there is no language delay. Whereas in autism, IQ can vary, can be anywhere on the scale, but there is also language delay. We'll come back to I better hurry, I should be finished. So when we're trying to understand what causes autism, the first thing we have to do is define it accurately, because if you have 100 children that have difficulties, intellectual impairments, and you lump them together, you're never going to find the cause of anything because they have different causes. Whereas if you define a condition clearly, then you can start making progress into what causes it. So at the moment we're still uncertain, but we're getting close to understanding what autism is. But this hasn't stopped people from making all sorts of claims about what causes autism. Everything from prenatal environment, ultrasounds in pregnancy have been blamed for autism, endocrine diseases, toxic substances, lack of oxygen, low birth weight. You've heard the story of the vaccination. It's all bunkum. All complete bunkum. But a lot of parents who are desperate to help their children, often and not able to judge that this is nonsense rather than real. So all of these causes have all been blamed. Refrigerator mother means a cold mother who's not. It's all bunkum. Complete bunkum.
And including by very intelligent, educated people. Correct.
Right.
How widespread myths can be.
Absolutely, absolutely. Now, when you're trying to figure out what causes a specific condition and you make an hypothesis, your hypothesis has to explain all of the features of a condition. And these are the features that any theory of the causes of autism has to explain. First, that there are severe functional impairments, that there's occasional amazing abilities in specific areas. Rain Man. Savants. Now, the savant story is the reason why it can't be a toxin. It can't be anything that is toxic. Because if you have something that damages the brain, you're not going to have someone who can do the amazing abilities that some of these kids can do with mathematics and things.
So the idea of savantism in regard to brain injuries, is that a myth then?
Well, I would think so. Yes, absolutely. Savantism is what happens. This is why these genes that control connectivity, if you have too many connections, unfortunately most of the time it scrambles the brain in most places and in most people. But occasionally, just by chance, the connectivity is correct just in one region of the brain, and it's so in excess that it can give you these amazing abilities. And this really is worth thinking about, because you wonder, has the brain got a potential to get even better than it is now? And the answer is yes, because if with time, if you have these amazing abilities, unfortunately at the moment it only happens in this sort of scenario where you have genes that are malfunctioning in connectivity and produce too many connections at a sort of random way. But if we could control that, you could have everybody being a savant in every area. Can you imagine that? Not yet. No. Now, the other thing that children with autism have is irritable bowel. How can a toxin explain irritable bowel? But what that's come up with, the people that don't understand this, is that there's the leaky gut hypothesis of autism. And it came from the fact that kids with autism have gut malfunction. You've got to be able to explain that there's a rapid increase in brain size early on in these children, that there are degrees of severity, there's a higher risk of epilepsy in these children, and you need to explain why the prevalence is increasing dramatically. Now, there's no time today to go over the evidence of, but if you choose to do the course, we talk more about this, what causes autism. The actual best proposed theory is that it's due to abnormal connectivity and that this is genetic. Okay? No, that in fact it's been shown that there are too many neuronal connections in local networks but reduced connectivity in long distance networks, and that the most likely cause of autism is genes. Okay, any questions? Thank you.
Thank you.